In this lecture, we are going to discuss about one-dimensional conduction problem in continuation with the last lecture. But this time, we are going to solve the similar kind of situation for hollow cylindrical and spherical systems. So it's basically one-dimensional conduction equation once again, but the solution is to be obtained for other two coordinate systems as compared to the previous one. So let us start with the lecture. I'm going to discuss about the hollow cylindrical conduction, then one-dimensional conduction in hollow sphere, then the analogies, respective electrical analogy for hollow cylinder and sphere. Of course, in the same fashion as it was discussed or it was done in the plane wall, same logic, same things can be extended. Only thing is the change in the formulae, which is required for obtaining the thermal resistance. With that change, we can get introduced to the electrical analogy for hollow cylinders and sphere. Then once again we'll talk about overall heat transfer coefficient in these cases and some closing remark with a summary. Let us start. I am Nitin Birud, working as associate professor in Sandeep Institute of Engineering and Management. Cylinder, hollow cylinder, as I told you that cylinder inner radius is say R1, outer radius is say R2. It is exposed to some fluid whose temperature is T infinity with heat transfer coefficient of H1. Consider a hollow cylinder exposed to a fluid at different temperatures for steady state conditions with no internal heat generation. Once again, same situation, steady state, no internal heat generation, and one dimensional. The appropriate form of the heat equation is 1 upon R d upon dr R into dt upon dr is equal to 0. Now, in order to find out the solution, we have to integrate it twice. So, if you integrate twice, and we'll get the general solution, and the general solution is in the form of temperature in the radial direction is C1 natural log of R plus C2. So, we have to find out the values of C1 and C2 using the boundary conditions. Now, applying the boundary conditions to the general solution, once again we are going to use the same boundary conditions, that is the known temperature boundary condition of first kind, that is temperature at radius R1, that is the inner radius of the cylinder, is Ts1, and temperature at radius R2, that is the outer radius of the cylinder, is Ts2. So if you put this boundary condition in these equations, that is Ts1, first boundary condition, Ts1 is equal to C1 into natural log of R1 plus C2. If you put the second boundary condition, it will be Ts2 C1 natural log of R2 plus C2. You can note the changes in the values of Ts and R1. Now, if you solve these two problems, two equations, we have got two simultaneous equations, and we have to solve these two simultaneous equations for two unknowns C1 and C2. Okay, C1 and C2, and if you substitute it in general equation, obtaining the C1 and C2 values and substituting back into the general equation would result into this type of equation. Now, this is the temperature distribution equation. This temperature distribution equation is Ts1 minus Ts2 divided by natural log of R1 upon R2 into natural log of R upon R2 plus Ts2, where R is the radius at which we are expecting the temperature to be calculated. So that radius you have to substitute the value here, and R1, R2, R2, Ts2, Ts1 are all these are the constant value. Only the variable in this case is going to be R. So once you put the value of R, which is lying between of course R1 and R2, we can get the value of temperature at any location within that radius, within that object. So this is how we can use this temperature distribution equation. In the similar lines, for the plane wall, we can use the Fourier's law. Of course, before that, temperature distribution is logarithmic, not linear. It was linear in the plane wall. You might recall that the temperature distribution equation was a straight line equation, but in this case, it is logarithmic. It is not linear. If the temperature distribution equation, that is this 1.29, is now used with Fourier's law to obtain the expression for the heat transfer rate, and if you do these calculations, you will get the final equation in this fashion, that is 2 pi Lk into Ts1 minus Ts2 divided by natural log of R2 upon R1. Now you can see that there are many common things in the equation obtained for the cylinder and for the plane wall. In both the equations, you might observe that Ts1 and Ts2, that is delta T, is present and it is in the numerator. Conductivity is also in the numerator. And then there are some geometrical parameters. In this case, natural log of R2 upon R1, and in the numerator it is 2 pi L. So it was K A divided by L into Ts1 minus Ts2 in case of the plane wall. So here you can see the change, 2 pi L divided by natural log of R2 upon 1. This will represent the geometrical things. Otherwise, K into Ts1 minus Ts2, this term is constant for both the things. Similarly, we can express this uh, conduction from this equation. It is evident that the radial conduction in the cylindrical wall can be calculated from this equation, and this once again can be expressed in terms of thermal resistance. Now, how to write down the thermal resistance? As you already know, it is thermal resistance is always equal to the temperature difference divided by heat transfer rate. So if you rearrange the terms in this term, Ts1 upon Qr, what will you get? This natural side, this natural log of R2 upon R1, this will go up, and this 2 pi Lk will be at the bottom, and you will get the final equation in this way. The thermal resistance for conduction in a cylindrical system is natural log of R2 upon R1 divided by 2 pi Lk. So using this simple equation, we can find out the thermal resistance for a conduction into a cylindrical system, provided we are having the dimensional, we are having the information about the dimension, and we are having the information about the conductivity of the material. So with this small information, we can calculate the thermal resistance for the conduction. Now, this thermal resistance can be used for finding, this equation can be used for calculating the thermal resistances for different systems. Maybe a single layer may be there, or multiple layers may be there, maybe composite system may be there. For the composite system also, we can use the same equation. Now, if a composite cylinder is there, now consider a composite cylindrical system, recalling how we treated the composite plane wall and neglecting the contact resistance. I am not considering the contact resistance now. Of course, contact resistance is going to be there, it has to be considered, and it is going to be in series with the resistances of the object. So there is no doubt about that. But right now, just in order to simplify the things, we can ignore the contact resistance. Whenever it is required, we can simply add it in series with all other resistances. So that's not a big issue. So this is the cylindrical wall. You can see that there are three layers now. Inside there is convection, outside there is convection. So totally three layers, three resistances in series for the layers, and two resistances for convection. So the entire circuit will become of five resistances, five thermal resistances. Out of that, two are for convection and three are for the materials or the conduction resistances. So if you know the temperature, inside temperature of the fluid and outside temperature of fluid, and if you are in a position to find out all the thermal resistances, simply you can use delta T upon total thermal resistance, and you can find out the thermal heat transfer rate in the radial direction for this. So what we need for finding out the problem, for finding out the solution of this problem, are the values of R1, R2, R3, the values of the inside and outside temperature along with the heat transfer coefficients, and the thermal conductivity of these respective materials. With this brief information only, we can find out simply the rate of heat transfer like this. The equation is in this fashion. This is the convective resistance, this is the convective resistance for the outer side, and all these three are the material resistance. You can see that how they are written. It is R2 upon R1 for the first layer. So outer radius of the layer is R2, the inner radius is R1, divided by 2 pi Ka. Ka stands for the thermal conductivity of the first layer. In the similar fashion, for the second layer, I am writing R3 upon R2. That is, R3 is the outer radius of the second layer, and R2 is the outer inner radius of the second layer, and then divided by 2 pi Kb into L. Kb means the thermal conductivity of the material B, or the second material. Then plus natural log of R4 upon R3. So outer radius is of the third layer is R4, inner radius is R3. So the respective layers, the radius of the respective layer is to be considered. Okay, so this is a simplified form of this equation, and it can be used for finding out the heat transfer rate in practice. So, what we need for finding out the problem, for finding out the solution of this problem, are the values of R1, R2, R3, the values of the inside and outside temperature along with the heat transfer coefficients, and the thermal conductivity of these respective materials. So with this brief information only, we can find out simply the rate of heat transfer. So The above result, once again, like the plane wall, we can write down this simple results into overall heat transfer coefficient term. And if you write it down in terms of the inside area means the inner cylinder area, and that inner cylinder area with respect to radius r1 is going to be 2 pi r1 into L, and we can write it down in this fashion. So this U, that is overall heat transfer coefficient based on the inner surface area. So if you use this inner surface area, you can everywhere multiplied by this term by 2 pi r1L, and you will get this. You can calculate the overall heat transfer coefficient based on the outer surface area. See here, the overall heat transfer coefficient on inner surface area is going to be different, and the outer surface area is going to be different because the areas are different. Remember that UA is a constant. U into area is a constant, but U is not a constant. U is changing with respect to the area, but product of U into the corresponding area is always constant for all the areas. Means we can calculate for R1, for R2, for R3, R4, whatever you want. You can calculate, but that overall heat transfer coefficient multiplied by the corresponding area is always constant, but U is not a constant in a cylindrical system. For plane wall, is the case was different because every area was same. There was no change in the areas. In radial system, Q is a constant. Rate of heat transfer through the system is a constant, but the heat flux is not a constant because the area is changing. At inner surface, the area is 2 pi R1 into L. At the outer surface, area is 2 pi R4 into L. So area is different, and that's why the heat flux at the outer surface is different, although the rate of heat transfer is constant. This is very, very important observation. You should remember this. Now we can repeat the similar type of calculations for a spherical systems. Consider a hollow sphere with inner and outer radius are exposed to different fluids at different temperatures as shown in figure. For steady conduction, we without no generation the appropriate form of heat equation. So let us consider a similar kind of system. Inner radius of the radius sphere is R1, outer radius is R2. The inner surface is at temperature Ts1, outer surface is at temperature Ts2, and the heat is getting transferred. We are ignoring the heat transfer in the other direction. So considering the radial heat flow only, the equation is 1 upon r square d upon dr, r square into dt by dr is equal to 0. Now this r square can be carried directly into this side and it will become 0. So it will be reduced to d upon dr, r square dt upon dr. So if you integrate it twice, you will get the temperature distribution equation in this fashion. That is T. You can carry out these integrations and you will get this C1 upon R plus C2. Now our interest is to find out what is the value of C1, what is the value of C2. For that, once again, we are going to use the boundary condition. The boundary condition is same like the cylinder. The temperature at R1, that is radius is equal to R1 is Ts1. Temperature radius is equal to R2 is Ts2. If you put all these boundary conditions into this equation, 1.35, you will get the results, and if you substitute the first boundary condition, it will be like this: Ts1 is equal to C1 upon R1 plus C2. Second boundary condition will yield C1 upon R2 plus C2. Now you have got once again two simultaneous equations in which two are random constants C1 and C2 are there. You have to solve them, and once you solve it for C1 and C2, the general solution for the temperature distribution will be like this, where this R is the radius at which the temperature is to be determined. So this temperature, this equation will enable us to calculate the temperature at any point in the object in between R1 to R2. Now we can use the same Fourier law of conduction. Once again, before that, the temperature distribution in radial conduction through spherical wall is also not linear. It is not logarithmic, but it is not linear in this case also. If the temperature distribution is now used with Fourier's law to obtain the following expression for the heat transfer rate. If you use this temperature distribution equation along with Fourier's law, finding out the temperature gradient and substituting back into the Fourier's law of equation, you will get this. The radial heat flow in a spherical system, hollow spherical system, is equal to 4 pi k in bracket Ts1 minus Ts2 divided by 1 upon R1 minus 1 upon R2. Once again, observation. K is in the numerator, temperature difference is in the numerator, and other terms. Here you can see 1 upon R1 minus 1 upon R2 into this 4 pi is representing the geometrical conditions of the object. So I'm just comparing, giving you the comparison so that you can remember and understand the things in a better way. Now this is equation 1.37. From this result, once again, we can rearrange the terms in terms of delta T divided by QR, that is the thermal resistance, and we can write down the thermal resistance in this fashion. So it is 1 upon R1 minus 1 upon R2 divided by 4 pi K. Or it can be simplified in this fashion. It is R2 upon R2 minus R1 divided by 4 pi K R1 R2. So if you just take the multiplication of this bracket, you will get that also. So this is the equation which is used for finding out the heat transfer thermal resistance for the hollow cylindrical system. Now, once again, the same logic, uh, electrical resistances in series and parallel is applicable to the spherical things also. So, spherical composites can be treated in the same way as composite walls and cylinders. Resistances in series, resistances parallel, finding out the total thermal resistance, equivalent thermal resistance, using with the total temperature difference to find out the total rate of heat transfer, or individual resistances for finding out the required temperatures or something like that. That can be done. Now let us have a summary of all the equations which you have got in the previous lecture and this lecture. We have started in the previous lecture with this equation. Then we have developed the temperature distribution equation, then the heat flux equation, heat rate equation, and finally the thermal resistance equation. A similar journey was there for cylindrical wall. So this slide is giving us the entire picture of last two lectures. For solving the problems numerical, this particular thing is important for us because we are interested in finding out the thermal resistances, individual values of the thermal resistances, and using those individual values of thermal resistances in series and parallel, whatever you can find out the network value, network to total thermal resistance, and using the total thermal resistance along with the total temperature difference, we can find out the rate of heat transfer in these things. So that makes the things more simpler and more clear. So this is what we have learned in this lecture. We started with one-dimensional conduction in cylinder. We have discussed about the electric analogy in the cylinders. Then we have discussed about the sphere in the same fashion along with its electrical analogy. And then in the last slide, I have to given you the summary of the one-dimensional conduction equation. In the next lecture, I'll be solving some of the numerical problems so that we'll get how to convert a real life situation into a manageable situation, how to apply the equations to it, and how to find out the solution and what we can comment about the solution. So next lecture will be discussing about the solution methodology using some numerical problems. Thank you very much.